Okay, this is part 4 of the sample problems for exam 1 for Math 2414 Calculus 2. Begin this session at 43 and we'll go all the way to the end, problem 56. Alright, now we're looking at volumes of solids of revolution. So we're trying this solid, we want to rotate it around the x-axis. So you see it has a picture here for us, but that would not be a hard graph to generate. We don't have to have the picture unless it was a really complicated graph, but you should be able to graph y equals x squared and y equals 2, then if you just kind of freehand it. Because it doesn't have to be perfect, and it will always be shaded, so it's trapped by the y-axis, x equals 0. Now what you have to look for, whether or not this is going to be a solid, when you revolve it, or is it washer, meaning is it going to have a gap or a space in it, or disk versus washer method, I should say. For example, if you look at this graph and you were sending it around the y-axis like so, that shaded region right here would have to be perfectly solid. In Cal 3 we call that a three-dimensional parabola. It's called a paraboloid. It would be a solid parabola. But look what happens when this graph revolves around the x-axis, which is what we're trying to solve here. So I just kind of drew a rough simulation of what it would look like on the other side. But you see that it's going to have this space in here, like so. Oh, well, okay, that's good enough. So that space, when it revolves around, that's going to be in there. So this is considered a washer method. So what we are doing is we are finding the outer volume, which would be the line. So if that line revolved all the way around to make a cylinder, then we would we'll subtract the empty part. So how far it is from the x-axis to the empty part, creating like an invisible volume. We'll subtract that, and by default that will leave us what we have. So here's the formula. So the outer function actually is the line, y equals 2. It's outer minus inner. Y equals 2, and the inner function is the x squared, the parabola. So we take 2 squared minus x squared squared. And the limits of integration, basically to figure out what that x value is, well, if you have y equals x squared, I didn't write it down here, whatever. You have y equals x squared and y equals 2, and set those equal to each other, you have x squared equals 2, which mathematically is plus and minus square root of 2, but obviously you see we're in the first quadrant here, so obviously it's positive square root of 2. So that line I drew right there is the x value of the square root of 2. And then, of course, 0 is starting at the origin. So let's see what we have. So pretty easy. So it'll be 4 minus x to the 4th. So you can still use a calculator to do that. That's fine. If you use a calculator, because the answers will probably be marked maybe in terms of pi, or they may be multiplied by 3.14, blah, blah, blah. But if they are in terms of pi, or I like that on a face-to-face class, I always tell people to answer it in terms of pi. So you actually want to not put the pi in there if you're integrating this manually, or calculator-wise, and then just tack on the pi with the answer. But this one's pretty easy to do by hand. It's not too difficult. A couple of basic power. We got some square root of 2 business to deal with here, but other than that, it's not too bad. And you end up with 16 over 5, or 16 pi over 5 root 2. Like I said, the main thing, these problems where they get messed up on tests, is not recognizing when it's a washer. So let's come down here. And it's basically the same situation, except we're going around the y-axis. So like I was saying earlier, this will not be a washer because it's going to be a complete solid when it goes around the y-axis. But now, when you go around the y-axis, you're now integrating in terms of y. So your limits of integration are y. So they would be 0 to 2 vertically. 0 to 2. and then you have to take your equation y equals x squared and solve it in terms of y, which is not that difficult. Just square root both sides, so x equals the square root of y. This one turns out being pretty easy. So then you just take pi times from 0 to 2, square root of y squared, which is y, which makes that 1/2 y squared, put in 2, put in 0, and we get a volume of 2 pi, because that one was a solid, so there was no empty part to subtract. Fantastic. Let's see what we have here. This curve, which I can put in the calculator, x cubed, horizontal line y equals 1. We're going around the x-axis. Very similar to the problem, very similar to 2 problems ago. Almost seems a bit redundant here, but that's okay. So it would be the outer, because usually you'll have a gap right there where I have the pointer when it revolves around. So it's the outer, which is the horizontal line, minus the curve. Yeah, very similar to that one. So it's, and x is going from 0 to 1. And you can solve that real easy. If y equals x cubed and y equals 1, x cubed equals 1, so x equals 1. That's where they would intersect. So you have 1 cubed minus x cubed squared, so you're basically integrating 1 minus x to the 6th. So it's x minus 1/7 x to the 7th from 1 to 0, and you have the pi there, so you end up with 6 over 7 pi. So this is very similar to 43. So now this one's going around the y-axis, and yeah, I could have cut this off at the x-axis as the border here. That's all right, but it's that shaded part right there. Yeah, it needs to be kind of a a closed, bounded region, or it won't be able to be done. So, all right, so we have y equals 4 minus x squared. So this will be a solid when it revolves around. No washer, in other words. I guess technically, when I say solid, it's going to be, everything we're finding is some sort of solid. I guess I should say solid, whether it's a disk method or a washer method, meaning will that solid have a hole in it or a gap in it. But this one's a solid by disk method, so we don't have to subtract. So if x squared equals 4 minus y, we take x equals 4 minus y to the 1/2. And vertically, we're going from 0 to 4. Pretty easy. Put 0 in there for x. You'd see that y was 4. And that square root square work out real nice because they cancel. And so we're basically just integrating 4 minus y because those two cancel. And we have 4y minus antiderivative y, which is 1/2 y squared. There's our pi, 0 to 4. And the answer is 8 pi. All right, now 47, we're moving on to arc length. Now, obviously, I have to be real careful. I should have put, yeah. Well, it's here. I'm going to go and copy this and move it up here. Now, I could ask a setup problem on the test, but obviously if I ask you to integrate something, it needs to be doable. In other words, you have to be able to do it. This one, not so much. Well, I should say that, well, numerical integration you could, but I have to, it needs to be something that can be done manually, even if you're not doing it manually, to make it fair for everybody. So there's a formula, so it's really easy to set this formula up, nothing to it. 0 to pi. So it's f prime of x, so the derivative of sine is cosine. And you see the formula, so it's the square root of 1 plus f prime squared. So it's just 1 plus cos squared, all under the radical. From 0 to pi, you can't simplify, you can't do anything with that. Now, if that was 1 minus sine squared, 1 minus cosine squared, you could do something about it. Because that would just be sine squared, and the square root of sine squared would be sine. But 1 plus cosine squared is not any kind of identity. So that's all there was to that one, just setting it up. Now here's one we're going to evaluate. So if y equals 2/3 x to the 3/2, we're going from 0, 0 to 9, 18, which we didn't really have to have the y components there. That's okay, the y coordinates. All we need is the x going from 0 to 9. And so the derivative of that, 3/2 cancels 2/3. You'll be left with x to the 1/2. So then the integral will be 0 to 9, 1 plus the derivative squared. So it's 1 plus x to the 1/2 squared. So that's just 1 plus x. So this is just a basic, whether you do it numerically or whatever. Works out beautifully because it's just u substitution, so it's not too complicated. It's not like any of the other integrals we've done from chapter 5. So it's just regular u substitution from Cal 1. So if I let u be 1 plus x, du will be dx. I'm always a big fan of changing the limits of integration. I think that's the way to go, because once you convert it to u, you never have to go back to x again. It's by far the best way to do it. So you put 9 in there. 1 plus 9 makes 10. 0, 1 plus 0 makes 1. So we go from 1 to 10, u to the 1/2. So just do the power rule. It's going to give you 2/3 u to 3/2. And from 1 to 10. So if we were in a situation that I was asking, wanted the answer to be exact, you would need to come up with this exact answer here. So just in case, because obviously the calculator is not going to give you this exact answer. It will only give you the decimal. So it's 10 to the 3/2, and then 1 to the 3/2 is 1. 10 to the 3/2 is fine with me, but a lot of answer keys would probably show 10 to the 3/2 is the same thing as 10 times the square root of 10. So those are equivalent. So if you saw the answer that way and wondered what I did there, they're the same. So that's not too bad. Here's another one. A little more challenging. I think we'll be all right. You have to kind of catch a factoring deal here, and you'll be all right. All right, let's see. So here's the derivative. So to bring the 3/2 down, cancels the 2/3, and then the exponent drops to 1/2. But don't forget chain rule, which says we have to take the derivative of the inside, right? I don't know why that's so close together. Okay. So the derivative of the inside, x squared minus 1, would be 2x. And so there we have it, x squared minus 1 to the 1/2 times 2x. So I put this in here because we're going to square all that. I guess I copied this and cut paste. Just bring it right down here so we can see it. Edit paste. There we go. So it's 1 plus all of that derivative squared. Now, because these two things are multiplied, so you always have to be careful how you do deal with squaring binomials and things like that. In other words, you can't square individually terms that are added and subtracted. In other words, if you had parentheses a plus b quantity squared is not a squared plus b squared, and you would be amazed to see how many times I see calculus 2 instead of doing that. But that is not correct. But see, look at these two pieces together, the 1/2 power part and the 2x. They are together by multiplication, which means I can square them individually, because if you have, if they're multiplied or divided, trying to draw here, well, it's probably a waste of time, but, it's supposed to be ab squared is, that you can do, would be a squared, b squared, if they're multiplied. Well, that's just lovely. Anyway, so I can square those two. Now, I can't go inside that parentheses where that minus 1 is, but nor do I want to. So the x squared minus 1 to the 1/2 squared is just x squared minus 1, and then 2x quantity squared, you got to square the 2, don't forget. A lot of people make that mistake. Another place people make that mistake is if you're looking at the first two problems where you're doing those triangle problems. A lot of times people, when they're building their triangle, they have to do the Pythagorean theorem. They'll forget to square the coefficient. So if they square like this 2x, a lot of times people, you'll see them square it and they'll say 2x squared. They don't square the 2. So now you got these two multiplied together. This looks kind of bad. But I'll distribute the 4x squared through the parentheses now that 1/2's gone. Remember, the only time you can distribute through parentheses is when you have a power of 1 where the parentheses are. So I rearrange this. I have 4x to the 4th minus 4x squared plus 1. And I can see where this will be a little bit tricky, but now that I'm showing you this, you can watch for this now and know. That part under the radical factors. In fact, it factors into a perfect square, even better. That's what we want. So this stuff in the factors into a pair of these. 2x squared minus 1 times 2x squared minus 1. And that's going to work out beautifully, because that's a perfect square. So the square root of 2x squared minus 1 squared, the square root will kill the square, so you're just left with 2x squared minus 1, which I didn't write that step. But anyway, so what I did from here to here is I'm just integrating 2x squared, 2x cubed over 3. Antiderivative of 1 is x. From 0 to 4, plug it in, and the exact answer is 116 over 3. So that last part might have been the trickiest part of the whole problem there, was just realizing that factored into that perfect square. So now that you know, that'll be real convenient in case that comes up. Let's see, number 50, surface of revolution. I want to mention this in my notes in 7.4. We only have to worry about, you can use the x formula no matter what. We'll do this in terms of x. I guess what I'm saying is, this is a little bit different than volumes of solids of revolution. Because if you're going around the x-axis, you have to use variable x. If you're going around the y, you have to use variable y. That's not true with the revolution, surface of revolution. You can use variable x to go around either x or y, or you could use variable y to go around x or y. But we'll just stick with x. So what that means is that when you're looking at my notes, and I'm going to go back and put something in there about that, is that just a couple of those problems, I set them up as if they would have been in terms of y and worked them out just to show that the answer matched. You do not have to do that at all. You can just stick with x. So the main thing to remember on this is, okay, we'll compare these. Nope, these are, now they're both x-axis. Let me see, do I have a y-axis coming up, hopefully? Oh, beautiful. All right. So you can use x's no matter which axis you're going around, but what this says, Rx is the distance between the F and the axis of revolution. Now there's in the notes, at the top of my notes for that section, I showed a little thing I copied out of the book. But all you have to remember is, if you're going around the x-axis, R of x will be the function what y equals, x cubed. You're going around it'll be whatever this is. So R of x and F of x are the same thing if it goes around the x-axis. If you are going around the y-axis, just use x for R of x, and you'll see that coming up here. That's why I scrolled down to look. So the 2 problems from now, we'll see that. So for this, R of x will be x cubed, and it's 1 plus the derivative squared, so it kind of shares that same thing as the arc length. And the derivative, of course, is 3x squared. So that gives me 9x to the 4th. I didn't write that, but you see I wrote it right here. Okay, this is very doable. It's perfect u substitution. Because if you let u equal 1 plus 9x to the 4th, you will get your x cubed that you need right here when you take the derivative. So it's perfect. Now, of course, I didn't see out the 1 over 36 here. Of course, you have to divide by 36. Looks like in the notes I didn't do this, but it looks like in a lot of these review exercises, I guess I figured left that step out. I figured by then people probably would realize it anyway. So it's fine. So it's 1 over 36. So I changed my limits of integration because that's what I always like to do. I think it's the best way to do it. So I put in 1 here. 1 plus 9 will be 10. put in 0, we have 1, so that way I never have to go back to x again. So this formula has 2 pi, unlike the volume that has pi. 2 pi, 1 over 36 coming from the du, and then it's just u to the 1/2 du from 1 to 10. So that gives me 2/3 u to the 3/2 using the power rule. You can simplify all this. 2 over 18 is 1 over 9. 9 times 3 is 27. So it's pi over 27. And put in 10, 10 to the 3/2, 1 to the 3/2. That's kind of familiar. Yeah, we had 1 and 10 earlier, didn't we? Because I remember talking about 10 to the 3/2 being the same thing as 10 square root of 10. Yeah, so I have to, if I'm having you integrate these, I have to make sure that they're doable without too much difficulty. So there we go. So you use the r of x is f of x whenever you're going around the x-axis. So here's another one. We're going around the x. Oh, no, I'm sorry. Wait. No, that was x. Okay, I did both. I think I missed one. Oh, excuse me. It looks like I missed one here, didn't I? Sorry about that. Back up here to number 50. This was a setup, but do not evaluate. But it's x-axis, so r of x would be what y is. So there's, so it's that 4 times the square root of x plus 1, and then you take the derivative. There's derivative y prime is 2x plus 1, the negative 1/2. So I put that in there as a square, and then I squared it out. But we didn't integrate this one, so it ends up being 8 pi. So that's the answer. No integral work necessary, but you can see that would. I'm not even sure if that's even possible or not. All right, sorry about that. So I missed that one. So now we've done 51. Now I knew there was okay, here comes the y-axis. So here's what I was saying. Every time you go around the y-axis, if you're using variable x, which we will do, we'll stay with variable x. Like I said, it's different. In my notes, I switched it over to variable y just to show, but different thought process. But here, it's just x. R of x is x. You see I got x right there. So the derivative of 4x squared will be 8x. Which means I have 1 plus 64x squared under the radical. So perfect u du. You let u be 1 plus 64x squared. Put my limit in there. Put 2. I get 257. Put 0. I get 1. So the derivative is 128 dx. So you see I have at least I color coded it to help a little bit. So there's 1 over 128 from the du. So 2 pi from the formula. 2/3 u to the 3/2. So that the pi over 64 times 2/3 simplifies into pi over 96. So it's 257 to the 3/2 minus 1 to the 3/2, which is just 1. So yeah, these answers are, aren't a thing of beauty, but they're not supposed to be. That would be the exact area of the surface if you revolved it. Now let's look at some work problems here. We'll focus mostly on the spring stuff here, but I just threw this one in there for the heck of it. So basically, anytime you have work, if the force is variable like this is, negative square root of x over 2, you have to integrate it from wherever the 2 points are you're going, because it's not constant force. If it was constant force, it's just force times distance. But we have to integrate this across that, the a 0 to 9, that is the distance. So that's just negative 1/2 x to the 1/2. So we just do the antiderivative. Not too much pain on this one. And so antiderivative of negative 1/2 x to the 1/2 will be negative 1/2 times 2/3 x to the 3/2. If I wanted to, I chose not to here, but I, sometimes I do this. If I wanted to get rid of that negative, I could have switched the order of the 0 and the 9, but I didn't do it for this one. And we have negative 1/3, 9 to the 3/2 minus 0 to the 3/2, which gives us negative 9. So whatever we're doing here, it's kind of, the force is not, we're not going the right direction, basically. I know it seems odd to have negative work. In Cal 3, we do stuff with work along, we use vector fields in space, and if it's obviously, if you're going one direction, if it's opposing you at enough force, you can actually not, you can have negative work if a force field's working against you hard enough versus the direction you're going. So I guess this force is going the opposite direction, but oh well. I'm not a physicist, so I won't. I'm just going to take it for what it's worth. It's -9 and move on. Spring problems. Here we go. Spring is stretched 0.5 meters with a force of 60 newtons. So take 60 newtons to stretch it out half a meter. How much work would be done in compressing the spring 3 meters from its equilibrium position? I think the wording is wrong in this problem. Once again, I'm not a physics person, but this is not designed to trick you here. But I would think if the stretch and the compress should both be the same thing. But don't overthink that on a test or anything. But that is bizarre. I would think that should say stretching. All right, so there's that right there. Stretch. So we have, so we're not worried about this anymore, stretched and compressing. So the 60 Newton force will equal K times 0.5. So that means K would equal 120. So that's our constant we need, the proportionality. So that means our force function is 120x dx. So the antiderivative of 120x will be 60 squared. We're going from 0 to 3. And plug in, so 60 times 9 is 540 Newton meters, 540 joules. On a handwritten test in a face-to-face class, I don't make you have to get the units right, like you would certainly have to, and should have to get to right in a physics class. But here I don't care enough. Just get the 540, and that's all right. You can worry about that elsewhere. So 55. Now, this is in my notes. Obviously, this kind of problem, you got to be careful here on this. So a force of 1,300 pounds compresses a spring from its natural length of 19 to a length of 10. So before I set this up, we can get the force part done first here. It's kind of all over the place here. Bring this up here. And so it takes 1,300 pounds to go to from its natural length, compressing it from 19 inches total down to 10. It means we moved it down 9. So that pretty much gives us this. K would be 1,300 over 9. Now, so this is the setting up the limits of integration. Obviously, the integration's easy because you're just integrating x, something times x. So that's kind of nice for these problems. But compressing it from 10 to 7. So a lot of people make the mistake of thinking the limits integration would be 7 and 10. But that's absolutely not correct. What you have to think of this, and like I said, go back and look at my notes for that section, is the limits of integration are how far you're compressing it, the length that's being compressed. So when it's if it's 19 inches total, and when you're at the 10-inch mark, that means you've moved it in 9. It's been compressed in 9. So that's the lower limit, 9. And then when you've compressed it down to where the entire length of the spring is 7 inches, that means that if the total length 7, you've compressed it to a length of 12. I mean, you've compressed not to a length of 12. You've compressed it inward 12. So you've compressed it. So it's a gap of 3, but you've moved it in 9, and then you're moving in to 12. So the limits of integration are 9 to 12, not 7 to 10. I'll put this up here, and okay, once again the units inch pound. So that's the big hurdle on this problem. I like to put that one on the test. It's one of my favorites there. So mainly it's interesting. Can you get, because the math is not difficult. So I need to at least have some sort of challenge on these problems and setting up the limits. So now you integrate 1300 over 9 x dx. So 1/2 x squared. The fractions reduced to 650 over 9. So 12 squared is 144, 9 squared is 81, and we end up 45, 50, whatever, inch pounds. Obviously, that's not a big deal. And number 56. So this one, to get our force function, instead of, to get our K, we're starting with a work amount instead of a force amount. But we can still get our K from there, too. In other words, if it's telling you it takes 80 joules to stretch it 0.5 from its equilibrium position, that's fine. We can still get K. That's the same thing as if they just would have told us what force it was to stretch it 0.5 meters. Then we could have got K that way too. Here we have to do an integral, no problem. So if it's stretching 0.5 from its resting point would be 0. So 0 to 0.5 kx dx has to equal 80. So 80 would equal 1/2 kx squared. So 0.5 squared is 0.25. 0 squared is 0. The 160 comes from multiplying both sides by 2. So I got rid of that 1/2. So 160 equals K times 0.25. Divide by 1, multiply by 4, and you get 640. So that means our force function is definitely 640x. Okay. So just a little bit different way then to get the force function. But once we have it, we're good. So we're going to be integrating 640x. Now, what are the limits of integration? So let's see if they try to trick us here. So we're stretching at 0.5, and then how much work is needed to go an additional 0.5? Okay, so that means you're starting at the first 0.5, you go in, and up to another 0.5, which would take it to 1. So you're going from 0.5, half a meter, another half meter to 1 meter. So we go 0.5 to 1 and integrate this, 640x squared over 2. 1 squared is 1. 0.5 squared is 0.25. So you have 320 times 1 minus 0.25 equals 240J. And that's the end of this video. Best of luck.